Okay, in this short video, we're going to talk about a more advanced topic on working with bootstrapping, but working with small data samples. So in the previous video, we talked about the process of doing bootstrapping. So the basic idea is to do resample, that sample with repetition. So of course, as you can imagine, when you have very small data samples, the quality will be quite bad because for example, you only have 3 samples. That means you only have 8 different combinations. So you're going to get a lot of repeat the same result. Then your quality of sample become really bad. So here we're going to demonstrate to you this issue, and then the potential solution to that. Okay, so here is the number of library we're going to use. Okay, so let's start from generate some data sample. Okay, so we assign a randomly. We do this because we want to make sure our result can be continuously reproduced. Okay, so but if you remove it, it will be changed. It will change every time. And the case here, we generate 9 data samples from a normal distribution, where the mean is 2, and then the variance is 1. And then we generate 9 data samples. Okay, so that's the first data set we're going to use. And then from this, the same sample, we just choose the first 5, and the first 3 data samples. Okay, so because in this case, we can better compare our result. So after generation, we can see that the first one is our 3 sample, and then the last one is our 9 sample. So basically, a 3 sample only get the first 3 data sample. And then the set of 5 samples is the first 5 sample from the set of 9 data samples. Okay, so that's our sample we're going to work with now. Okay, and then if we do bootstrapping, for example, we want to calculate mean coming from these different data sets, sample sets. Then because we want to repeat to do it, so basically we just make our bootstrapping as a function. So this code is the same as our previous video where we implement our sample, but instead of instead of writing as a normal script, we make it a function so we can repeat it we can continue to use it. Okay. So for example, we want to generate from our for example, our first set of only 3 samples, and then that's the result. And then we produce 5 we perform 5 bootstraps. Okay, we perform 5 bootstraps. That's the result. And every time you get one of the values. So you can see you only have 3 samples. So very often you get repeat. You repeat your value. Okay. And then that's a mean you get. So you easily get some the same mean from here. Okay. So so that's the idea. So now let's make 10,000 times bootstrapping from each of the data set, and then let's look at their mean and also the distribution of their mean, and that's the result. That's a result. So that's a result coming from the set with only 3 data samples, and then the one from 9. So you can see when you work with very, very small data sets, your distribution from your distribution is very, very discrete. It's very, very discrete. Okay, that's 3 points are the 3 at your data sample is very, very discrete. Because you only have 3 samples. So as I say, there's only 8 different combinations. So your result is really, really limited. Okay. And then when you start to move the set with a higher number of samples, you can see it become more and more continuous. especially when you have when you use the set of 9 samples. You can see that the mean you produce is very smooth. Okay, so we can see the result look more reasonable when your data sample are and when your sample size are 7 or 9, so they're much smoother. But when we use 3 and 5, the shape is the general shape is okay, but the whole overall distribution is very discrete. It's not smooth enough. Okay, and then so the combination of sample mean you can obtain is also become very limited. So it's not good for you to estimate the uncertainty or the confidence interval. So we want to know, is there any better way that we can allow us to work with small data sample? Okay, so before we talk about this method, let's first revisit the bootstrap method with another example, with a simpler example here. Okay, so now assume we have an array with value 1 and 2 and 3. Okay, so instead of a very complicated, more complicated flow number, you work with integer 1 and 2 and 3. And then the same, we do 5 times. We do 5 bootstraps. Okay, so every time we generate a resample data coming from this array. And then here what to do is we count this array. We count each item of this array. We count how many of them are chosen from this bootstrapping process. And here is the result. For example, when we have first resample array, it's 1 and 2 and 3. That means these 3, 1 and 2 and 3 in each position or each item are chosen once. But the second resample array is 2, 2, 2. That means the number 2 at this value, the second item are chosen 3 times, and others were not chosen. They are chosen 0 times. And then 1, 1, 2, that means the first value is chosen twice, and then this second value chosen once, and then the third value was not chosen. Okay, so this kind of the count of each value are chosen this process, and then that's the corresponding mean calculate from this resample array. So we can see that different. So we can kind of look at the bootstrapping process in a different angle. So basically bootstrapping. So basically bootstrapping can be modeled as you have a limit data sample. So you're counting each of the data sample, how many times, what's the count of each data sample are chosen. What's the count? So we look at it in a different angle by we try to represent the number of times that a given entry or different item are chosen. Okay, so this is how we can kind of look at the process in this way. Okay, and then actually this chosen process, it actually looks like you make draw from a multinomial distribution with size n, and each of item have the 1 divided by n has the same probability to be chosen. Okay, so multinomial. So basically, for example, you have 1, 2, 3, 4, 5. You have 5 items, and then each of them have equal. So 1 divided by 5 chance to be chosen. That's multinomial distribution. Okay, so so we can model this above process by using a multinomial distribution that's supplied in SciPy stats. So in this multinomial distribution, first we need to assign how many items do we have, how many entries do we have. Okay, so in this case, for example, if we work with our array, so that means we have 3 items, and then each of them has 1/3 of chance to be chosen. Okay, they are equal, they are equivalent. Okay, in multinomial, you don't have to have equivalent probability. but the bootstrapping process it looks like a multinomial with equal probability. Okay, so this operation is equivalent to is equivalent to a list like this. Okay. Okay, so so for example, 1/3, and then you times 3. That means you generate a 3-entry list with 3-entry list, and each of them has 1/3 value. Okay, and then so from this multinomial distribution, and then we generate 5 random sample, because we do 5 times 5 bootstraps. So 5 random sample. That's the same as you're doing 5. Okay. Um, so we can see the sample draw from this multinomial distribution basically look like this. It's 111, 111, 102. So it's just like our assigned count. Okay. Then then of course we divide by the total number of our draw. Sorry, we divide by but here for example, here is a count, and then we can further convert into relative frequency because we're looking at probability. So divide by 3 because we totally have 3 data sample. So 111 means each item's chosen probability is 1/3, and 102. So 1 is 1/3, 1 is 2/3. Okay, so we are converting our count to relative frequency. That's it. Okay. So you can see now. So you can see now. You are actually, so from this count, because average is actually can be seen as number 1 count once. So 1 times 1, and then 2 times 1, 3 times 1, divide by 3. Or it can be looked at as 1 times 0.3 plus 2 times 0.3, and then 3 times 0.3. And then you can get this mean. Okay. So basically, when you want to calculate bootstrap, mean from bootstrap, you are first you are actually sampling the relative frequency of each entry to be chosen. So you just need to after sample the relative frequency, and then just need to times each of these entries value to their relative frequency. Then you get the mean. So you get the mean. Okay. So that suggests that the bootstrapping process actually can be modeled by this multinomial. Okay, multinomial distribution. So basically, the bootstrapping average is just a weighted sum of your samples. Okay, and then it draw from a multinomial distribution. Okay, so we can further calculate the mean from the by working with this density, so we can get the mean. So this is very, very similar to basically exactly the same as from the bootstrapping we show above. However, we can improve this. Because multinomial still is very, very discrete because it's chosen from this very discrete count. Okay, so it's still discrete. So that's why. So this multinomial process explain when we work with small sample, we don't get very smooth pattern. We don't get, because our weight is very discrete. It's basically just 0, 0.3, 0.6, and 1. That's all the choice we have. Okay, so multinomial distribution kind of limit our relative frequency or our probability of each entry to be chosen to this 1, 2, 3, 4, this 4 potential probability. So they are very discrete. There's no other choice. So the idea here is, can we relax this discrete restriction? Can we relax to make this become a more continuous version of bootstrapping method, or can we have more choice on this? Okay, so basically, so actually, yes, we can do that. In fact, there is another distribution that's kind of the continuous version of multinomial distribution. Okay, so it can also generate within the interval between 0 and 1, but it doesn't confine to a final set. For example, final set, that means you only have 1, 2, 3, 4, 4 potential probabilities. It can generate a continuous one, more continuous one, and doesn't limit yourself to this 4 probability. And this distribution called uniform Dirichlet distribution. Uniform Dirichlet distribution. And now we can make an example when you use Dirichlet, and then again you assign your sample, and then you generate a number of so you assign how you want to make sure the chance of being chosen is the same, okay? And then you generate based on this Dirichlet distribution, and you can generate phi random variable set. Okay, so it's equivalent as doing phi bootstrapping. And you can see the value generated by Dirichlet sample, they are not that discrete anymore. It has higher flexibility. So instead of limiting itself to only these 4, it has much more variation here. And the sum, it maintains the overall probability equal to 1. Okay, so that's Dirichlet. So now instead of using multinomial, we can redo our bootstrapping, but instead of using multinomial, that changed to Dirichlet. Okay, and then the same, we use our very simple array with 3 values, and 1 and 2 and 3, and that's the mean we get. So you can see there's much more variation in this result. Okay, so now let's go back to our original sample data set, our original this data sample. This 4 different 4 set of sample that with different data sample size. Okay, so now let's go back to our script. But however, this time instead of use the original bootstrapping method, we use Dirichlet to help us to generate this relative frequency for each value. And then the same, we do 10,000 times bootstrapping. So we generate 10,000 random variable samples. And then that's the resulting bootstrapping result. Here we call it Bayesian, okay? We call it Bayesian because we subjectively assign a distribution to them. And then we use our data to correct them. So that we call it Bayesian method, okay? So the upper row is the method, is a result resulting from when we use Dirichlet, uniform Dirichlet distribution. And then the lower part is the original one. So you can see we can produce much more variation of our result, and then it can eventually lead to a better estimate of our confidence interval. Okay, so as we mentioned, this is a more advanced implementation of bootstrapping, and then we want to tackle the issue when we have small samples. Okay, so I hope you remember this method. You don't need to remember all the detail of implementation, but one day when you have small samples, you may come back to look at this script, and then instead of using the original bootstrapping, you may consider to use a uniform Dirichlet to help you to produce a much better estimate of your confidence interval from small data samples. Thank you.